Hey everyone, and welcome to this explainer. Today, we are decoding the invisible rules that completely decide whether an atom is just going to sit there quietly or if it's going to release world-changing energy. We are taking some seriously dense reactor physics and, well, explaining it in a much simpler way so it actually makes sense.
So I really want you to consider this for a second. Imagine you're holding two atoms of uranium. They look absolutely identical. They behave chemically the exact same way, but one has this microscopic, almost imperceptible difference in its weight. We're talking a tiny, tiny fraction heavier, and yet no way that tiny difference completely alters its destiny. It turns one into a massive fuel source that powers our entire electrical grid, while the other is practically inert. So what's going on here? Why does that happen?
All right, let's dive into our source material to find out. Now, I have to admit, when you first look at textbook pages like this, filled with terms like scission point and Coulomb repulsion, it can look incredibly intimidating. It's like a solid wall of impossible math. But honestly, don't worry about it. We are going to unpack this whole thing together step by step. Let's start by just stripping away all that jargon. At the end of the day, the text is talking about one very specific thing: fission. To put it simply, fission is just the process of breaking a stressed-out, super tightly packed atomic nucleus apart so it can finally relax into a much more stable state. Think of the nucleus like a painfully overstuffed suitcase. Fission is that exact moment the zipper finally bursts.
Okay, moving on to the atom's tug of war.
To understand how that atomic suitcase bursts, we have to look at the microscopic battle happening literally right now inside every single atomic nucleus. The textbook describes this as an absolute tug-of-war. On one side, you've got the nuclear attractive force. Think of this as the super strong glue trying its hardest to pull the core of the atom together. But on the exact opposite side, you have Coulomb repulsion. See, because the pieces inside the nucleus are positively charged, they naturally want to repel each other. They are aggressively pushing apart. So you've got the glue desperately pulling everything in and the electrical force aggressively trying to push it all out.
Which brings us to crossing the fission barrier.
So how does the pushing force actually win this tug-of-war? The source visualizes this almost like trying to roll a massive boulder up and over a really steep hill. You start way down at the bottom, that's point A, where the nucleus is still intact, but it's starting to deform. Then you push it all the way up to the absolute peak, which is point B. The textbook calls this the scission point, and it's basically the point of maximum stretch. If you can stretch that atom just a tiny bit past point B, the glue completely snaps. The Coulomb repulsion just takes over and shoves the pieces all the way down to point C, which is total separation. And boom, you have fission.
Now, you'll see the term critical energy pop up here. And really, you can just think of this as the energy toll you have to pay to get our atom from point A all the way up that hill to the scission point at point B. It's literally the cost of admission to cross that fission barrier. No toll money, no fission.
Next up, the odd-even neutron effect. Okay, so the atom needs a push to pay that toll. But where does that pushing energy actually come from when a nuclear reactor is up and running? Well, this second source page gives us the answer, and it introduces some pretty dense academic concepts like the liquid drop model and pairing energy. But buried right inside this paragraph is a fascinating, almost kind of cute microscopic rule that perfectly explains why some uranium powers cities and some just doesn't.
Let's explain this in a simpler way. Let's call it the neutron buddy system. It turns out subatomic particles absolutely have preferences. Neutrons desperately love to be in pairs. They love even numbers. So if you have an atom with an odd number of neutrons, it's energetically agitated. It really wants a buddy. If you shoot a single neutron into that odd nucleus, it suddenly creates a happy pair. And the text explains that completing this pair releases a massive burst of what they call binding energy. But actually, if you add a neutron to an atom that already has an even number, that new neutron becomes the odd man out. The atom is annoyed, and it releases much less energy.
So let's look at why uranium-235 splits easily.
Let's take this very simple buddy system rule and directly apply it to our two types of uranium to finally solve our mystery. We're looking at uranium-235 versus uranium-238. Based on the data, uranium-235 has an odd number of neutrons. It is just sitting there basically begging for a buddy. Uranium-238, on the other hand, already has an even number of neutrons. All of its buddies are perfectly paired up. So, what exactly happens when we toss one extra neutron into uranium-235? Remember that energy hill we talked about? Well, the data from our source tells us the critical energy toll it has to pay is 5.3 MeV. But because it's catching that desperately wanted buddy, it gets a massive energy payout of 6.4 MeV. Think about those numbers. Because its internal energy payout of 6.4 is way higher than the 5.3 toll it needs to climb the hill, it effortlessly blasts over the fission barrier and splits instantly.
Now contrast this with U-238. Its energy toll is 5.5 MeV, but because its neutrons are already perfectly paired up, forcing a new awkward third wheel in there gives it a measly energy payout of just 4.9 MeV. That 4.9 completely fails to pay the 5.5 toll. It simply absorbs the neutron and gets hopelessly stuck at the bottom of the hill. Zero fission.
Let's tie this all together with the raw data from Table 2.1. The absolutely crucial part is right there in the right-hand column, threshold energy. Threshold energy is essentially the extra outside help you need to force a split. Because uranium-235 gets more than enough energy from just finding a buddy, the extra threshold energy needed from the outside is exactly 0.0. It splits readily, completely naturally. But U-238 stubbornly falls short by 0.6 MeV. This means you'd literally have to smash a neutron into it at incredibly high speeds just to make up that difference, which makes it totally terrible for sustaining a standard reactor chain reaction.
Which leaves us with this pretty incredible thought to wrap up our explainer today. We build these massive, multi-billion-dollar nuclear power plants. We mine thousands of tons of earth, and we engineer arguably the most complex machinery in human history. Yet, when you strip away all that dense physics jargon, this entire global power system relies absolutely entirely on a microscopic, subatomic particle just wanting to have a buddy. Without that odd even pairing effect giving uranium-235 that extra energetic push over the hill, our reactors just wouldn't work at all. Isn't it absolutely wild how the biggest forces in our world are completely governed by the smallest, most relatable rules? Think about that the next time you flip on a light switch. Thanks for joining me on this explainer.